Welcome to December 30th LeetCode Challenge. Maximum difference between node and ancestor. Given the root of a binary tree, find the maximum value v for which there exist different nodes a and b, where v equals the absolute value between a dot val minus b dot val, and that a is an ancestor of b. A node A is an ancestor of B if either any of the child of A is equal to B, or any child of A is an ancestor of B. So this is a common binary tree type of question. If you didn't get that explanation, I'll go through some examples here. So let's say we have this root tree here, this tree named by root, and it's a binary tree given by 8, 3, 10, 1, 6, null 14, null, null 4, 7, 13, and then it ends, right? And we want to find the maximum difference between node and ancestor. So that means that a node is node A is an ancestor of B. Either of these conditions exists. So A is equal to B, or a child of A is an ancestor of B. So that means that if we take the absolute difference between the ancestor, which is, if this is for instance, considering this number 3 here, the node that holds the value 3, it's a child of the ancestor 8. So the absolute difference between that is 5. Similarly, if we take the absolute difference between the node here are just some examples actually, between ancestors and child nodes. So if you take any absolute difference between the ancestor of any child node, then you want to find the maximum difference, right? And then we find that the 8 minus 1 will give you an absolute value difference of 7, and that's the output because that's the largest difference that you can make from all the possible differences between the ancestor and the child. Alright, because for instance, we cannot have 1 minus 10 here because 1 is not an ancestor, it's not a child of 10, right? 8 is a child, it's a descendant of 10. I mean, 1 is a descendant of 8, therefore 1 is an ancestor of 8. Or 8 is an ancestor of 1, I should say. And that's pretty much how it goes, and you're trying to find the largest difference between any of the node and ancestor. Here's another example here. So we find that given this binary tree here, which looks kind of odd, at 1, null, 2, null, 0, and 3, we know that the maximum difference between ancestor and a node would be this number here. Maybe the absolute difference between 0 minus 3, which is 3, right? And that's pretty much it. The constraints is that the number of nodes in the tree range between 2 to 5,000, and the value of the node itself range between 0 to 10 to the 5. Let's look at some hints here. For each subtree, return the maximum min for each descendant. So yeah, we could do that. So there's a couple ways of doing this. We could use a breadth first search or depth first search, which are recursive algorithms, which are great for solving these binary trees. I'm going to try to do an iterative approach. Yeah, let's do that. So the iterative approach has got to take care of keeping track of the maximum and the minimum node value that we have iterated down a path. Alright? It's very similar to a depth first search type approach, except we don't recursively go through it, we just do it in one pass. And we're going to do it as such. So we're going to develop a queue, call it Q, and it's going to be a list of values. A list of a list, and we're going to take a root here, root dot val, and then root.val again. Ideally, these are going to hold two of the parameters where, how to describe this? It's going to hold the minimum current min and the current max of the value as well. I mean, I think I could probably do that right now. Yeah, I'll leave it the way it is. And then we're going to have an output. And that's going to be assigned to 0 because initially, if we have an empty set, then the difference is 0, right? That's going to be our output. So while our queue exists, we are going to find the node where we're at, and we're going to find the maximum and then the minimum. Value, and we're going to do that from queue.pop 0. So ideally, the node itself is going to be the root value. We're going to have a current maximum value and current minimum value. We just have some placeholders there for now. And then we want to be able to find the difference, the absolute difference, so we call it diff. And that's going to be the absolute difference between max minus min. Maximum minus minimum. Oh, I spelled this wrong. Alright, that's going to be our difference as defined right here. And next thing we want to do is update our output to be the max value of our difference. So it's either going to be our current answer or our newly calculated difference. Right, and this is our output is going to basically find the max between the output we have currently, which is 0, or if the maximum difference is higher between min and max, then we're going to take that as a new output. Right, it just iterates through while Q exists. So we have everything kind of set up so far, and the next thing we need to do is basically iterate down the path of the left node and the right node. So to do that, what we want to do is do an if statement. So if node.left exists, right, if it's not null, what we're going to do is q.append. So we're going to append certain thing, a couple things to it to update our queue so far. So we want to update that with the, well, obviously it's going to be an array. It's going to be node.left because we are on the left side of the node, which is the value, not the value, the node we're on. And we want to basically find the maximum between the node.left value .val and the maximum number that we have so far. And we're also going to store the minimum as well. Alright, minimum from node.left .val and minimum. Alright, and that should be good for the left side node. Next thing we want to do is do a similar approach to our node.right. If node.right exists, what we're going to do is take the queue and append our node.right to it, and taking the max between the node.right.val and our maximum. Right, we want to pair basically. I'll finish typing this down, then and then take the min between our node.right.val and our minimum. At the end of all this, you want to return our output. Let's run the code briefly to check, and I'll kind of go over this component here. node. Alright, looks promising. So basically from if you're with me so far, if the left node exists or the right node exists, what we're gonna do is append the queue what we have so far, and we want to take the node on the left side, and when we want to find the max value, we're comparing the max value between where we're at currently, so the current node we're at on the left side, and we want to compare it with the max value of its descendant, right? For instance, if we're at current node number 3, we don't, and the bigger the value difference is, of the ancestor, that's the one we're gonna care about. So that's what we want. We want to find the biggest number and the smallest number between the descendant, the node, and the ancestor. And that's why we keep track of them on both sides, right? We keep track of them between the current maximum and the number we have, find the maximum thing there. We also want to find the smallest number, what we have so far, traversing down the list, the node of each tree. So we want to find the current node we're at and the minimum. And we keep on going through each node and then down the path and finding the largest number and the smallest number, and then therefore we keep on updating our difference, right? The larger we can get the maximum difference, we update our output, and that's the thing we're going to return once we traverse the entire tree. Let's submit it. So there you go, accepted. Time complexity is big O of n because we have to traverse through each node on the tree. At the end of the day, like, this is not very fast. It's only like about 15% of beating whatever else, right? But space complexity, we are storing a lot of space here by storing everything inside a queue. So we only have a max, three numbers inside each of these, right? 3 nodes, I should say. So it'll be big O of constant space, right? But time complexity is pretty high because we have a while loop, and each while loop here has its if statement to go into as well. Alright, there you go. Have a great day, guys.